In the previous video, we looked at section 13.3 and we were looking at partial derivatives. Partial derivatives, their meaning in the context of tangent lines. Okay. So we showed in the previous video, and what I will summarize here now is that if you have a function, z is equal to f of x and y, that has been given to you. Okay? And you have been given also a point, x naught, y naught. Let's just call this our point of interest. Point of interest. Okay? We can feed this point into the function to get a point x naught, y naught, f of x naught, y naught. Okay. And we can then find the curves on this surface that go through that point. And this is the curve on surface through, and we'll just call it, this is the curve on the surface, and let's just say this is the curve in the y direction. Okay, we can see this curve and it's pointing in this y direction. If you were to look at it from the top, this curve would be moving parallel to the y-axis. Okay, and here is our curve on the surface in the x direction. Okay, and in the previous video, we showed how to compute these tangent lines. Okay, this right here is this dotted line is the tangent line to the surface, and this tangent line is also pointing in the y direction, and the other one is similarly the tangent line in the x direction. Okay, so the formulas that we essentially developed is that if you want to look at a tangent line in the x direction, it's going to be a vector valued function in one variable. This is the tangent line to the function f of x comma y at the point x naught, y naught, f of x naught, y naught in the x direction. It's kind of a long thing to say, the tangent line. Essentially what you need to do is you need to compute your curve in the x direction and evaluate that at the point x naught, y naught. What I should say is that we should compute, let me erase this real quick. We want to compute the curve in the x direction at a particular time, okay? And then you want to take the derivative of that same curve, evaluated at t0, and then you would multiply that by t, okay? Now t0 in our case, t0 is often, we're going to just choose it to be 0 because of the way we've constructed this problem, in the sense that when you write down your lines through this point x naught, y naught, at t equal to 0, your curve in the x direction, when you put in 0 for t, you will get the point x naught, y naught, f of x naught, y naught. It'll go through the point right here that you want it to go through. So essentially what we've got here is just the general form for our tangent line is the point plus the direction vector times the time. So this is, I want to show some Mathematica demos at this point so we don't have to do as many computations by hand and we can just kind of focus on the ideas involved. But what I want you to focus on is these lines down here that go through this given point x naught, y naught. You'll see these curves on the surface. We will see these tangent lines. These tangent lines will be in red. The curves on the surface will be in black. You'll have a function. And then we'll see the significance of the partial derivatives in the context that we're looking at. So let me bring in Mathematica at this point. Okay. Okay. This is just a little bit smaller, but I do want to have a place to write in case I need. Okay. So let's take a look at what we're looking at. I'm looking at a function of two variables, x squared minus y squared. I've chosen a point of interest. It's the point x naught, y naught is 1, 2. And when you put that point 1, 2 into the function, you get 1, 2, negative 3. So here's what we're looking at. There's our surface. And we are looking at the point right there at the intersection of these two crosses. It is at the point 1 in the x-axis, 2 in the y-axis, and it's negative 3, so it's below the z-axis, z equals 0. So there's our point. Okay. What do you then do? We compute a curve on the surface in the x direction. Okay. So our curve on the surface in the x direction is this black curve right here. Okay. And my claim is that, notice that t is equal to 0. So if you put 0 into this curve, t equals 0 into here, you will get the point 1, 2, negative 3. So this curve at the particular time t is equal to 0 is that point right there where all these curves intersect. Okay? Now that was by construction. We created that curve on the surface, right? We created the curve on the surface by doing the following. We did x naught plus t. We did y naught. And then we did f of x naught plus t comma y naught. That's where we're getting this curve right here for this function. So notice that our x naught was 1. So x naught plus t is just 1 plus t. And y naught is just equal to 2. So that's what we're seeing here, 1 plus t, 2. And this part must be the function evaluated at 1 plus t, comma 2. And that's where you're getting this. So this curve is not so mysterious where it's coming from. It is just the curve, these straight lines through the point 1, 2, projected onto the surface. Okay. Now, the next thing that you wanted was these tangent lines. The red are the lines which approximate those black curves there at this point. So the way you would do that, if you want the curve, the tangent line to the curve in the x direction, here's our curve in the x direction. When you want to look for that red line right there, we would need to take the derivative of our curve, the derivative of this with respect to t, okay? And then evaluate at t is equal to 0. That makes sure that you're doing your arrow, your direction vector at this point when you evaluate at t equal to 0. You then put t0 into the curve, which we know that'll give you 1, 2, negative 3, because that's what you're supposed to get for the point that it goes through. So here I can see that right now that if I let t is equal to 0, this object that we have goes to the point 1, 2, negative 3, which was the point. And this is of the form of a line, and the direction vector of that line is 1, 0, 2. Okay, so we have an example here that when you compute cx0 plus the derivative of that curve, evaluate 0 times t, this is your point P, this is your direction vector t. Put those together and that makes a line. And that is a line in the particular direction x, because our direction vector here was 1, 0 for that line. Okay. And so if you write this line, I think you can see we have an example that it is 1 plus t, comma 2, comma minus 3 plus 2t. You should be able to see that's of the form 1, 2, negative 3 plus 1, 0, 2 multiplied by t. So this number 2, where does it come from? What is that number 2? Okay. There's two ways to think about it. It's the derivative with respect to t of the function x naught plus t, comma y naught, evaluated at t equal to 0. That's where you'll get the 2. You'll recognize that as method 2 for computing the partial derivative. So this is simply partial derivative of f with respect to x at the point x naught, y naught. So you can see here that this number in the direction vector for that tangent line, the third entry is simply the partial derivative. That's where this number 2 comes in. Okay. Now, if we switch our focus to the other line here, you're going to have a curve in the y direction at time 0. You're going to take the derivative of that curve, evaluate at time 0 times t. This is what we're going to call our tangent line in the y direction, okay, where cy of t, okay, is simply x naught, comma y naught plus t, comma f of x naught, y naught plus t. If you were to plug this formula into the function x squared minus y squared equal to your function, you should get that curve right here, and I will leave you to check that. Again, notice that the curve evaluated at 0 should just be the point 1, 2, 1, 2, negative 3. That means that this curve in the y direction, let's see, there's our y direction now, that same curve, this curve right here, different curve, still goes through the same point. Okay. What's its direction vector? C prime of y0. The direction vector for that line is, for its tangent line, C prime of 0, I should say, C prime, the curve in the y direction, the derivative of it, evaluated at t equal to 0. The direction vector for that line is 0, 1 in front of the t, and then there is a minus 4 here. Where's that minus 4 coming from? That minus 4 is coming from, it's the partial derivative of f with respect to y, evaluated at the point x naught, y naught, where x naught, y naught is 1, 2. And that's something you should check for yourself to convince yourself. So that's, the partial derivative is giving you one of the numbers out of the 6 that make up this tangent line. The first 3, so you can kind of view your tangent line as as something that you need to fill in. Oh, there we go. You can think of your tangent line as having a lot of entries to fill in. Maybe I should make this a little smaller. Okay, these are pluses, by the way. I got to be careful with my t's. So notice that here's where you need to put the point. So this tangent line, for example, L sub y, you have the point 1, 2, negative 3. That's because this is the point that the line goes through. Because when you put in t is equal to 0, you want this line to go through that point. These other numbers right here, these are where you are getting your direction vector from. Your L sub y, since the direction of this line is pointing in, the tangent line is pointing in the y direction, you need to have a 0 here in the x entry, you need to put a 1 here. And the last entry you need to fill in is some number. There were 2 ways to find it. You could use method 1 or method 2 for computing partials, right? But no matter how you compute your partial, the number that goes here is f sub y evaluated at x naught, y naught, okay? Which in this case is f sub y. Your x naught is 1 and your y naught is 2. And that would give you the number that goes right here into that third entry of your tangent line. So that is the geometric significance of the partial derivatives. If you were to change the function, okay, let's go change the function now. Okay, say cosine of x times y, and choose your point of interest to be the point pi, and then let's let the y value be 0, let's say. Let's see what happens here. See this interesting plot. Okay. Let me rerun it. Okay. All right, so let's see what we've got here. Okay, there's your surface. Okay. The point of interest that we picked was pi 0. Okay, so let's rotate this so we can see the x-axis. The x-axis is right here. So this is pi for x, 0 for y. That was our point of interest that we picked right here. We then computed the curve on the surface in those directions. Here's your curve on your surface in the x direction. So that would be this curve. Okay. The curve in the y direction, that would be this curve. Here is the formula for it. So take a look at what we've got here. What they're saying here is that our z value for that curve on the surface in the x direction, it looks like our z value is always 1. Okay. The curve in the y direction, that's this curve here. It looks like its z value changes. It changes with the cosine function. Okay, so that's why we can see here are the two curves. One is black, straight line, and the other one wiggles a little bit. Now, when you compute the tangent line, what I'm looking at here, the tangent line, okay, has 3 pieces. 6 pieces. The tangent line. Okay, it is a line, L of t. It has 6 pieces: blank plus blank t, blank plus blank t, blank plus blank t. Sorry, I need to make that a little bigger. Okay. According to this, our curve in the x direction, okay, looks like it goes through the point pi 0, 1. Pi 0 and 1. Okay, that's the point that it goes through. Okay. The direction vector. What's the direction vector? Okay, what is the direction vector? It looks like it's only 1 in front of the t here in the x entry. 0, because that means this 1 and this 0 make it the x direction. And there's no t in the z entry, so you have a 0 here. So this line only points in the x direction, and its partial derivative, we then conclude that the partial derivative of f with respect to x at the point pi comma 0, I'm going to conclude that that is this number right here. It should be 0. And you should check that answer. Check this answer via whichever your favorite method for computing partial derivatives, method 1 and 2. Okay. If you look at the tangent line in the y direction, again, there should be 6 blanks to fill in. Blank plus blank t. Okay. Okay. Let's look at the y direction. Oh, sorry, shoot. The curve I was looking at here is the, I'm sorry, this curve, that's our x direction right here. So our curve in our x direction, that's this curve right here. No, that's okay. It's always at a z value of 1. That's good. Okay. Now let's look at our y direction curve. This one, our tangent line. We can see that it looks like this. What is its equation? Well, we can see that the line in the y direction, it goes through the point at t is equal to 0, pi 0, 1. Okay, pi 0 and 1. That's the point that it goes through. You can see that right here. And then its direction vector is 0, 1, and then it looks like we have a 0 for that also. So I think I can see from this 0 right here that the partial derivative of f with respect to y evaluated at pi comma 0 is also 0. And again, you should check that. Check via method 1 and 2. Method 1 and 2 or method 1 or 2. Okay. So those tangent lines don't look very interesting. They have the z value is not changing. The z value of those tangent lines is flat. Okay, it's the same z value. Okay, I think something more interesting would happen if we changed points. Let's try pi divided by 2. Okay. So all I'm going to do here is move to a different part of this surface. I'm going to move to the point pi, x is about 3, and y should be 1.59. So we should be moving somewhere over here to the point 3, 1.59. We should see something like over here on the surface. Okay, and there we go. Okay. There again are your curves from the top. They look like straight lines through the point that you're interested in, but when you show the curves on the surface, there are these squiggly black lines. Here's your curve in the y direction. Here's your curve in the x direction. And I will leave you to look at these numbers and see if you can, right here, the ones from the function down to the lines and the tangent lines in the x and y direction. See if you can understand what these numbers are computing. Okay, so for example, like, do you understand that from this formula, L sub x, could you look at this formula for the tangent line and tell me how much this function, how much this tangent line in the x direction, right here, there's your tangent line in the x direction. Can you tell me how much it's changing, this function is changing at that point in the x direction? Okay. Could you do that? The answer should be f sub x evaluated at the point pi, comma pi over 2. We should see the answer right on the screen here, and this is something that you should check by doing the computations. But I'm looking right here at the number in front of the t of my tangent line in the x direction. So the answer you should get is 1/2 pi sine of pi squared over 2. That's the answer you should get for f sub x, evaluated at pi over 2. F sub y evaluated at pi over 2. Okay. Looks like this number is a negative number, indicating that this tangent line in the x direction, both tangent lines have negative slope. They are sloping downward if you can get the axes to match up right. So this is, I need them to increase. So here's x. Okay, yeah. So left to right, this line has negative slope. Oh wait, sub x. So I'm looking at the right one. This function seems to be going positive. So compute that number out on your calculator, and maybe for some reason it comes out positive. Let's compare f sub y, the function partial derivative of f with respect to y at pi over 2. I should see that answer as right here, the same answer, except without the half, minus pi sine pi squared over 2. That should be your answer. And I'm looking at the number in front of the t on the z entry of the direction vector. So both of these you should check via method 1 and 2. Okay. And we'll do more of these problems in class. Enjoy.